Alright, welcome. So this video is going to talk to you about Verilog. Verilog is a hardware definition language. And the goal here is to get you some familiarity with hardware definition languages in general, Verilog in particular. And up front, let me point out that HDLs like Verilog are extremely powerful, potentially extremely complex to use. You can spend years becoming an expert at working in a language like this. That's not our goal here today. Okay, our goal is simply to give you some basic familiarity with Verilog and basically get you on the air, get you started working with a tool chain. So you need a set of tools to work with this, and the example I'm going to use is Icarus Verilog. Icarus is freely available, and it works in both Windows and Linux. This is all going to run a lot nicer if you're in Linux, where you're working on a command line that you're comfortable with. But you can also do this from a DOS shell if you like. So if you go to Google and just Google iVerilog or Icarus iVerilog, it should bring you to an Icarus link, iverilog.icarus.com. And over there, if you click on Quick Links, you'll see some download options. So if you want to download from Windows, click on this off-site link, and that takes you to a page where you can download the appropriate version. But as I say, this is going to work better with just doing this off of Linux. And Linux installations come with Icarus Verilog as one of the install options in the package manager. So go ahead and install Icarus on whatever system you're using, and let's start talking about Verilog. So what is Verilog? It's a hardware definition language. It's a way to describe a circuit, and this makes it fundamentally different from a programming language. A language like C, we write code that basically represents a series of steps we want to execute. So do this, and then do this next thing, and then do this third thing, and then if this condition is true, do something else, and so on. That's not what Verilog is. Verilog is defining the physical structure of a circuit. It's a hardware definition language. And we've got to keep that in mind because Verilog code looks a lot like C code, but it's fundamentally different. And we'll get into some of those nuances in a later talk. But for now, let's just jump right in and start doing some basic Verilog. So I have a file here. Verilog files end with a .v extension. So I have a test0. And test0 is pretty short. It's 10 lines of Verilog code. This first statement is used for simulation. It's saying we want to simulate with 1 nanosecond or 1 picosecond resolution. That's boilerplate. You can sort of put this in the beginning of all your Verilog code and not worry about what it means. So module is an important keyword. Module is followed by the name of a module, a piece of hardware that we're defining, followed by parentheses containing the inputs and outputs to this circuit. So in this case, this circuit has 3 ports associated with it, A, B, and X. And then there's a semicolon at the end. Double slash starts a comment just like C. Everything is case sensitive just like C also. So this is defining a piece of hardware that we're calling test1, and it's got 3 connection points to it, A, B, and X. These next 3 statements describe what A, B, and X are. They're wires, and we'll just worry about wires for now. But A and B are inputs, and X is an output. So there's a directionality to these ports. And the one real piece of Verilog code in here is this assign statement. Assign X equals A ampersand B. Now this ampersand is an AND statement, again just like C. And we're setting X equal to the AND of A and B, but this keyword assign is an interesting one. Assign is basically saying take what's on the left and connect it by a wire to what's on the right of the equal sign. So this will actually say, hey, I want to take an AND gate, that's the ampersand. I want one input of the AND gate to come from A, that's an input to our module. Another input to come from B, that's another input to our module. And I want the output to go to what we call X, which is another port on our module, in this case an output port. So this line is really the only thing we need to define an AND gate, and the other stuff is set up. It's defining inputs and outputs. Everything tends to end with a semicolon except the keyword end module, which ends what we started with module. So that doesn't have a semicolon. And certain things like if statements, things where we're going to have collections of statements, won't have semicolons. The rules are a little weird, but you get used to them pretty quickly. All right, so here's our first Verilog module. It's called test 0. And we've written that we need to compile it. And to compile it, we're just going to use the Verilog command. So you can say Verilog and you can get a short help on it. And in this case, we're going to say Verilog and we're going to name an output file, which is test 0. And we're going to say let's compile test0.v. And we do that and we don't get any error messages. And what we've got is a file called test0. And if we look at test0, it's a compiled description of this Verilog code. So you can see it's human readable, but it's really kind of meant for a computer to ingest. Okay, we don't normally work directly with this. What we would do next is we would simulate this. But this by itself doesn't do anything. It's just an AND gate. So simulating an AND gate makes no sense. We need to specify inputs and outputs. Okay, and that's going to be the subject of our next video, which is dealing with what we call a test bench. So check that one out next.